Part B, what is the time for one revolution? The time for one revolution. It actually has a specific name. Part B, what are we trying to find? Nick?
Distance around the circle?
No, that would be a distance. We're looking for a time. Right? We're looking for a time to go all the way around once, through one full cycle, if you will. Matt?
No, I don't know.
We get to review so many things in this problem. It's wonderful. Wheatley. It is called the period. The time for one full cycle is the period. So let's start with the equation for angular velocity. Remind me, Spiro, what's the symbol?
It's an omega.
Omega. The equation for angular velocity, Isha, is?
Omega equals delta theta over delta t.
The change in angular position over change in time. Good. So what we're trying to find is the period. So if we set the time equal to the period, what is the change in theta equal to? Aurelia?
Is it
2 pi radians. So we have the equation angular velocity equals 2 pi over the period. We can multiply this whole thing through by the radius. We get radius times angular velocity equals 2 pi times the radius divided by the period. What is the radius times the angular velocity equal to? Radius times the angular velocity. It is equal to, Emma?
Tangential velocity.
The tangential velocity. We have the tangential velocity. We have the radius. We can solve for the period. The period is going to be equal to 2 pi times the radius divided by the tangential velocity. So 2 pi times 0.1 divided by the tangential velocity, 8.254665 times 10 to the 6th. The time for one full cycle. -8. Okay. And that's in seconds. So if we prefer, we could say 76.1. What kind of seconds would it be? 76.1. Wow.
Micro.
Microseconds?
Nano.
Leah?
Nano.
It's actually nano. Micro is -6, so this is going to be nano times 10 to the -9. So nano seconds. Doesn't take very long because it's moving pretty quickly.